Hi, and thanks for the invitation to give you this presentation on cryo-atom probe tomography of battery materials. This is work that has been pushed by some colleagues in the atom probe group at MPIE, especially Dr. Seho Kim, and with Mahanda Singh and Leonardo Auta, well, two colleagues working on battery materials, and Raju also contributed with helping with some TM especially. And there's also some work that I will present that was pushed in our computational materials design department on the DFT side in the group of Christoph Freisold by Dr. Shyamkat Nagaru. And some of the experimental work was joined with the group of Ingo Manke at Helmholtz Zentrum Berlin with a collaboration with Kong. For a little bit of context now, battery, when we think about it, is a device that has typically three sides, a cathode, an anode, and an electrolyte, with the transport of charged species from one electrode to the other electrode during discharge or during charge. And the electron traveling from one side to the other during charge and discharge and able to either use this to power devices, for example. Then in the other case, you need to actually supply power to get it stored into the battery. But when we think about materials science of batteries, we need to also realize that cathodes and anodes are also materials in many ways. So over the course of this cycling, charging, discharging, cycling, many things can happen. We can have secondary phases, for example, inside of one of the electrodes, can have boundaries, grain boundaries, phase boundaries, can have also defects forming, dislocations, for example, cracks that can form. And all of these grains can also, for example, turn out to be removed completely from the sample, interact with the electrolyte, and ultimately, the way the atoms are arranged, the composition of these different electrodes, the presence of potential impurities, and the evolution of all of this over the course of the charging, discharging cycles must have an effect on the properties, the physical properties, and hence on the cycling performance. Typically, for people like myself who come more from the metallurgical background, we like to think of many possible techniques that we can use to actually provide insights into the composition and structure of materials at a range of scales. And what the group that I lead actually is specialized in is atom probe tomography, which enables this to fit within this small corner where we can look at high detection sensitivity, so up to, and especially for lead species, down to tens of ppms, and with a spatial resolution that's typically better than a nanometer, looking at features that are in the range of tens of nanometers. What is atom probe tomography? In atom probe it's a technique in which we have a specimen shaped as a sharp needle. The sharp needle here is actually subjected to a high voltage and maintained at low temperature, typically a few tens of Kelvin. At the apex of the needle, on the surface, the atoms that are subject to a high electric field induced by the DC voltage here can turn into ions and be hence repelled away from the surface because of the effect of the intense electric field. They are not pushed out and fly in random directions. They follow well-defined trajectories that are defined by the distribution of the electrostatic potential inside of the microscope. And we can collect all of these ions that we have generated from the specimen surface by a position-sensitive detector. So the detector will record the impact of each of the ions that we have generated during the analysis. The field evaporation process is thermally activated, so typically I can control the time at which an ion is formed either by using short laser pulses that are going to heat up the specimen for a short amount of time, or by maintaining the specimen at a base temperature by using high voltage pulses that are going to increase the magnitude of the field for a short amount of time. And then it means that I know when the ion started its flight, I know when it was detected, I can retrieve its time of flight, and based on the time of flight, I can identify its mass to charge ratio. And by combining all of these informations, I can deduce from the mass to charge ratio the elemental nature, and I can use the detector coordinates to progressively, using a projection law, build a three-dimensional point cloud in which every single point that you see is one ion that was detected, identified, and repositioned in 3 dimensions with a resolution that is better than a nanometer in X, Y, and Z. Here we have carbon segregated at 2 different facets of a single grain boundary in a silicon polycrystalline silicon photovoltaic cell. So comparison to transmission electron microscopy, typically, again, our specimens are thin, so we can use those as a TM inside of the TM to provide some imaging. So here you have the electrons going straight through the specimen. We can see some contrast pertaining to precipitates in this precipitation hardened stainless steel, austenitic steel, sorry. We can even perform high resolution STEM, for example, in high angle annular dark field. You can see the disordered matrix, the ordered precipitates. We can see contrast pertaining to the difference between those. And then when we stick this specimen afterwards into the atom probe, we can complement all of these pictures by counting how many atoms of each of the different species we have in every single one of these different microstructural regions, if you want, between the precipitate, the matrix. We can go and measure their composition. So what about batteries now? Well, about 12 years ago, we had a colleague of mine at the University of Sydney who was interested in looking at some lithium titanium oxides that can be used as anodes in batteries. And we got some prepared specimens, got some data. As expected, the sample contained lithium and oxygen and titanium, and we could also collect some molecular ions of titanium and oxygen. All of this seemed fine and dandy. The detector maps that we were getting were quite homogeneous. However, during the reconstruction process, what we could see was always a high concentration of lithium towards the end of the needle, towards the top of the needle. And this was really quite reproducible, and we could not really understand what the problem was at the time. A few years later, there was this report by Guido Schmitz's group in Stuttgart of tungsten needles on which a thin layer of lithium-containing glass had been deposited. And they were reporting that the field that was generated, in this case at the end of the tungsten needle actually, that was traveling through the layer of glass could induce the migration of lithium. Even at the very low temperature that we use, the field could actually drive the lithium to come out of the specimen towards the top surface. And so performing the analysis had become really challenging because we could not really see where the lithium was. Inside of the structure, it was already coming out. There were also other reports of similar issues. So in a different specimen configuration now, where we have a support and the active material containing the lithium on the top, so similar to what we had done with the lithium titanium oxides. And for example, in this case, it was lithium iron phosphates, and they were reporting on lithium losses. Some other reports were talking about this electric field driven lithium migration, forming these hotspots on the detector. And the lithium is just what is detected in this case. We don't really detect any of the other elements for quite some time. Yet there were a couple of interesting reports also back in the mid-2010 and like earlier in the 2021 articles reporting on the lithium distribution in some of these cathode materials, primarily nickel, manganese, cobalt oxides. And so why did it seem to work? And it seemed to not only work, but also match with results that they were expecting from other techniques like TEM. So they must have been doing something right, or we must have been doing something wrong. And we wanted to test whether the lithium coming out was potentially due to defects from the specimen preparation, for example, some additional heating. Maybe there was something else. So we wanted to deploy the latest frontiers in atom probe research, meaning going full cryo. At MPIE, for the past 6-7 years now, we've been developing this infrastructure where we have a glove box that can be operated either in argon or nitrogen. Typically, we operate it under nitrogen conditions with extremely low moisture inside of the glove box. Then we can transfer through a UHV cryo suitcase into a fib, and then from the fib into the atom probe. And the idea is that we can take samples, for example, in this case, we are considering pure sodium, which is very air sensitive and moisture sensitive, put it inside of the glove box, transfer it onto an atom probe sample holder into the suitcase, from the suitcase into the plasma fib, and then inside the fib perform typical lift out. In this case, we could just dig the typical trenches, come in with the micro manipulator, lift it out, deposit it on a support, shape it as a needle, and then run these samples actually. We've used the similar protocol to make needles out of ice. So in this case, we are using the plasma fib not for a lift out, but for digging trenches and leaving a pillar in the center that we then shape as a needle. The water is just brought there on the top. This is inside of the atom probe in front of the local electrode after transfer under UHV conditions and at cryogenic temperature. And we can see a whole lot of different molecular ions of water coming out of this very small ice needle. So we decided to try to prepare specimens from NMC 811. It's a commercial powder. We made specimens through the suitcase, going from the glove box through the suitcase into the fib, made lift outs at room temperature, and then sharpened the specimens at cryogenic temperature, transfer them at low temperature into the fib, into the atom probe through the suitcase. We were very hopeful, and it did not work. And so we could see the same problems as before, where we had lithium coming out, just basically field evaporating purely lithium for quite some time, and then sometimes a little bit of the material underneath. So this really was quite disappointing. After several rounds of optimizations, we managed to get data that was almost okay, but we still had the traces of electric field driven migrations towards the specimen apex. So all in all, this was seen as a failure. So going back to the drawing board and scratching our head a little bit, we wanted to get back to what can we do to make this work. And if we consider again this configuration of the specimen, what we always expect when we're analyzing non-conductive materials is that the surface defects combined with the bending of the bands associated to the intense electrostatic field that we apply will provide enough surface conductivity to shield the penetration of the field of a substantial distance. And the electric field, in principle, we're expecting is really expressed just really on a very thin layer at the surface and primarily at the apex of the needle, towards the apex of the needle. But if the shielding is not really sufficient, then the field will start to penetrate quite substantially. And if that's the case, then effectively, yes, it could drive some degree of migration or diffusion of the lithium out of the material. And this would happen towards the top, but also potentially from the sides. And then there's a field gradient from the sides to the top, so you would actually drive lithium coming from the shank up to the end of the needle. And then you're establishing a gradient between the core that is still lithium rich and the edges that is lithium poor, and then you have almost a constant supply of lithium. So the question is, can we shield? Can we prevent this from happening by suppressing the penetration of the field? So going in this direction, we started using a setup that Seho Kim developed over the course of the past few years, whereby he's using a co-electrode deposition method where we are embedding particles into a metallic matrix, and we are going to use this as a substrate for typical analysis through fib lift out. So here you can see we have a copper substrate with deposited particles plus nickel on top. And then in this case, we just did a slice and view in the fib, so we just deposited a bit of platinum on top to protect them. In this case, we bought some commercial lithium titanium oxide, same composition as we had seen in the first example. And in the TM, they look more or less cuboidal-ish. And in the atom probe, we actually found many of those particles dispersed in the nickel matrix. And for the analysis of each of those particles, we could see that the lithium distribution was homogeneous across the particle. And more or less the composition was what we would have expected. So this was a good sign in many ways. However, if we consider again what had been published in the past, they didn't do this. They did not have a thin layer that was deposited on top. And so we went back to the samples and tried to reproduce what they had done. So was it simply that they transported the sample in air and prepared the specimens at room temperature? So we did the same thing actually. We just went back, took NMC 811, prepared specimens at room temperature, and then ran them into the atom probe after transport through air. And we could see that the lithium distribution was homogeneous along with the oxygen, nickel, and other metals. So it seems that the transport in air was actually the key in this case. So to understand a bit better why this could be happening and helping us, we stopped the run, put the specimen outside in the room, put it back into the atom probe, analyze it again, and we could actually see clearly a difference in the surface composition with a layer of what looked to be hydrogenated species on the surface. And if these species cover the entire specimen, they might actually provide enough of a change in the composition to help with the surface conductivity. And there was some literature on nickel oxides after hydrogenation that actually showed that there was an increase in the surface conductivity because of this surface species. All in all, this was just good signs that potentially we could find ways to analyze these materials in good conditions. So we started looking at other NMCs, some silicon anodes. In both cases, we could see grand boundaries. Started also looking at some solid-state electrolyte, and there's been some work coming out of Aachen recently, or Jülich, that are demonstrated feasibility. We also looked at frozen liquid electrolytes. And as I said before, we could actually run pure sodium, for example, and we also started looking at the SEI, so these interfacial regions that form between an electrodes and the electrolyte. For today, I'm going to really just focus on a recent example on which we did a bit more work, the silicon anode. So let's talk about the microstructure evolution of single crystal silicon during lithiation and delithiation. In this case, we mounted a typical battery with lithium metal, silicon as a silicon wafer along the one-on-one orientation as an anode, and a liquid electrolyte containing also lithium salt. And so while silicon is potentially very interesting because it can normally bond with more lithium than the graphite that is used in most commercial batteries today. However, during the formation of these lithium silicides, there's a lot of deformation taking place because of the volume expansion associated to the phase transformation. And these are going to lead to quite a lot of structural defect and microstructural defects and potentially cracking. And this has been reported in the past, never studied on the scales that really we can look at. All of this was reported in a recent paper. So again, we made the battery, we cycled it, and you can see in this CV test that there's basically first lithiation actually captures quite a lot of lithium, and as we proceed with cycles of lithiation and delithiation, the amount of lithium we can actually accommodate inside of the silicon anode just drops substantially. And over the course of lithiation, delithiation, we want to look at what are the different stages that are proceeding, and what can we gain as insights from cryo-atom probe. So the battery was opened inside of the glove box, mounted on a clip holder that is sitting on a puck, so typical atom probe sample holders, and then transferred through the suitcase into the fib for specimen preparation, and after specimen preparation, transferred through the suitcase into the atom probe. So we use the same geometry as I've mentioned before for the ice. We have these trenches made from the plasma fib, and then the needle is left there in the center. Put this into the atom probe. We analyzed initially just the frozen electrolyte, and we see a number of different carbonate chains. But amongst these carbonate chains, there was also the trace of silicon, and silicon ions individually spread across the matrix. And here we can actually go back to the literature, and it was proposed that any residual moisture when the battery was made that remained would actually decompose the LiPF6 salt, and this would form HF, and the HF can actually etch the surface of the silicon anode and cause some corrosion of the silicon anode itself, and then the silicon would then end up in the electrolyte floating around, which is exactly what we see. And after this first analysis, we stopped the run, put the specimen back into the fib, took it back into the atom probe after some resharpening, and we could see then the analysis just of the silicon. At this stage, there's been zero cycling. It's just depositing the electrolyte onto the silicon anode, and already we have some insights that are interesting in the composition of the electrolyte itself. After one cycle inside of the electrolyte, we detect a number of fragments that are silicon-rich. So these are pulverized fragments. We also find an increase in the concentration of these isolated silicon ions. And if I zoom in on this fragment, I can see again silicon in the core, and then all around are silicon and oxygen species that are formed surrounding the silicon-rich core. Again, this could be in part related to HF formation, but also on the oxidation of the silicon on the surface of the silicon itself. After 25 cycles, we can see we targeted just right the interface between the electrolyte and the anode. We find that there are multiple grain boundaries that are formed. There's surface species that are also silicon and oxygen rich. And so this would also potentially be similar to the ones we found on the surface of these fragments that were floating. Inside of the grains, we actually detect some lithium, about 10 ppm of lithium. From the literature, we might assume that these have been trapped because of remaining vacancies inside of the silicon crystal. And we can also find phosphorus segregated to the grain boundaries, and the phosphorus comes also from the decomposition of the lithium salts that we have seen. So it's really broken down into phosphorus and fluorine completely separately. So this silicon 111 becomes polycrystalline. Some of this was known, but we could really now measure like very low level of phosphorus at these grain boundaries, which would affect their mechanical resistance against further lithiation and delithiation. And there's also some lithium that is remained trapped inside of the silicon, which might also affect the pickup of lithium afterwards. So many interesting results, many questions still to answer. Okay, so this is a nice example. Let's talk about some remaining challenges for us to tackle. I've mentioned this before, but this electric field assisted diffusion is actually causing a number of problems when we have lithium inside of a material. But when we want to look at lithium by itself, pure lithium, we actually end up with this being the norm, and this is kind of problematic. So we tried many experimental conditions, and pure lithium analysis seems to be almost impossible to control. We ran other low evaporation field materials, for example, gallium or indium gallium alloys. And same process, prepare the specimen, the PFib, run into the atom probe afterwards, and we can see that we managed to get good data. But it's very sensitive to the base temperature. So at 30K high voltage pulsing, we get good analysis conditions. We can see poles, we can see atomic planes. As soon as the temperature starts to increase, we start to see these hotspots forming, and at 100K, it's all gone. And in laser pulsing mode, we actually get no signal whatsoever. We need to really go into high voltage pulsing mode to be able to field evaporate gallium. So we turned to our theory colleagues, and they did some DFT calculations of the pure lithium under high electric field conditions, looking at this structure, and we can see that as the field increases, there's a point where the lithium atom is actually barrier free. It can just leave and be field evaporated. That's been the norm in the sort of theory that they've been doing. However, there's also a very strong decrease in the energy barrier for surface migration, and this is an example where before the field is reached that would allow for field evaporation, the lithium atoms become free and can start to move around to another site on the surface before leaving. And this happens at much lower fields than what you would need to remove the atom from its current site. So this is going to happen. So we are really hitting a physical limit for the analysis of lithium. So just to conclude, we've pushed the development of cryo-atom probe in part to look into these types of materials. In principle, now atom probe can really supplement and provide complementary insights from TEM or XPS or SIMS that other groups have been using to look into these battery materials, and particularly problems that we could look at are the macrostructural evolution and looking at, for example, the corrosion degradation behavior of some of those materials. At some stage, however, there's still some complex physics that we need to understand to really push the limits of what we can do. I want to thank you for your attention and thank all of the funding agencies that have been helping us support and make this work possible. Thanks.